central to the work that we do. We couldn't have made the discoveries that we've made without having people to analyze very large data sets and to help us find hidden trends within them. Now, when I was growing up, I was somewhat insulated from the idea that women or girls couldn't be scientists because I came from a family of scientists. And when I was in college, I learned that not everyone had that privilege. I hope that all of you women data scientists or aspiring data scientists will truly feel that you belong in the field, because I believe it, and your participation is absolutely essential for us to bring the full benefits of data science to solve the big problems in humanity. So just as I was so fortunate to have a family that created an environment where I could believe in myself as a scientist, I'm hoping that you all have the confidence to pursue your dreams and that you help the generation that follows you in the same way that hopefully someone of my generation can be of help to you. Good luck with all of your work.
Good evening, everyone, and welcome to the Datathon Workshop series. I am Rashmi Mendis, Ambassador of WITH Sri Lanka, your host for today's workshop. We are thrilled to have you as we embark on this exciting journey of learning and discovery. Our workshop series promises to be a valuable learning experience, and we have some fantastic guest speakers lined up to share their insights. I kindly request all the participants to rename yourself with your first and last name. Before we dive into today's workshop, let me give you a brief overview of what WIDS is. It is an organization with the aim to empower women to reach their full potential in the field of data science. We elevate and celebrate the outstanding work of women on global scale, fostering respect, collaboration, connection, and visibility. The WIDS community creates access to programs, content, and resources that inspire, educate, and support, so that vibrant voices and ideas can be shared in the world. Let me give you a brief introduction of the WIDS Global Datathon Challenge. Gilead Sciences is the sponsor for this year's WIDS Datathon. The challenge theme for Datathon 2024 is Equity in Healthcare. We are thrilled to announce that it's the 7th annual WIDS Datathon competition. Participants are asked with the developing a model to predict if the time for the patient to receive their first treatment for their diagnosis is within 90 days of their metastatic cancer diagnosis. Datathon is designed to help you discover whether disparate treatments exist, to understand the drivers of those biases, such as demographic and societic factors. The primary goal of building these models is to detect relationships between demographic of the patients within the likelihood of getting timely treatment. The first challenge is health inequality, as it has become a global challenge. Addressing the challenge has an extensive positive impact on women's health, which is a key for societies and economies to thrive. We have provided a rich worldwide dataset which contain treatments, insurance provided about patients who were diagnosed with breast cancer from 2015 to 2018. The timelines of the Datathon Challenge 1 started January 2024 and ended in March 2024. And the Datathon Challenge 2nd started in April 9, 2024 and ends on June 7, 2024. The WITS Datathon is open to individuals or teams of up to 4. At least half of each team must be individuals who identify as women. You can connect with global WITS Datathon participants with WITS Datathon Slack, WITS Datathon Kaggle, and WITS Datathon Workshops. I welcome you all to be a part of Worldwide Challenge Datathon 2024. Without further ado, let me introduce today's distinguished guest speaker, Ms. Sandamali Wickramasinghe, PhD candidate from City, University of London. She is an expert in the field of data science. We are honored to have Ms. Sandamali here with us today to share her knowledge and insights on data science and machine learning. Ms. Sandamali, the virtual floor is yours. Please enlighten us with your wisdom and expertise.
Hello, everyone. So thank you for the introduction. And so my name is Sandamali, and today I'll be discussing about feature engineering and selection. And so while doing the talk, I encourage everyone to ask questions. So then we can actually be more interactive during the session. So I'll share my screen. Okay, give me a second. Okay, hope you guys can see the slides and hear me clearly.
Yes, we can see and hear.
Thank you, Rashmi. So I'll start now. So today we'll be discussing about feature engineering and selection. And throughout the talk, we'll be talking about importance of feature engineering and how we can do feature transformation, about several feature selection methods, and about some dimensionality reduction methods. Sorry. Okay. So when we are working on a model, most of the time, data scientists spend their time to do the data cleaning and preparation. And the topic we are talking today, the feature engineering and selection, it's something belong to this data cleaning and preparation process, which we do before building our model. So why this is important? So I'll explain these things clearly while we are discussing the techniques. But for now, feature engineering and feature selection actually helps us to increase the accuracy of the model. And if we have like higher number of variables in our data set, this helps us to build simple models and also to reduce the complexity of the models. And also it helps us to select most relevant features to include in the model and also for better interpretation. So first I'll discuss about feature engineering. So feature engineering is creating new variables using the raw data we have in the data set. So we start with raw data, we build up some features, and then we build the model. So I'll first give a very simple example to feature engineering. So suppose this is a part of a data set about houses. So in the first column, we have the size of the houses. And in the second column, we have price of the houses. But just looking at this data, we can't say much about our houses or data or anything about it. Now I have added a different column, a new column, which I engineered using these two columns. So this is price per square feet. If I plot this, you can see that house 3 is somewhat different from the other houses. So we actually saw this because we engineered this new column, which actually can give a general interpretation about the data. So that's a very simple example to feature engineering. And there are various methods we can do feature engineering: aggregation, calculation, transformation, and encoding features. So aggregation means, so we create new instances by aggregating information across categories. For example, this could be averages, sums, minimums, or maximums. This is an example. So we can actually create a new value by calculating the total purchases which happened in last 3 years. And also we can do feature engineering using calculations as we did in our previous example. So it's about combining multiple variables in our data set and building a new variable using the relationship or interactions between them. So we can either multiply, divide, or do some things with the existing variables and create a new variable. And also there are other two techniques, transformation and encoding features, which I'll be discussing in our next slides. So moving on, this is the data set I'm going to use in today's session. So this data set is about strokes. The response variable is this one, the variable stroke, and it's a binary variable. And I have other few variables, 3 numerical variables, which are age, average glucose level, and BMI. And all the other variables are categorical variables. So I'll be using this data set to do the coding part in throughout the session. So I'll explain feature transformation. So feature transformation is something we need and something very important when we are building up models. So depending on the assumptions of a model, we may need to transform our features. So there are two types of very common transformation techniques, standardization and normalization. So standardization is scaling a feature and feature so that the mean of the feature would be 0 and the standard deviation would be 1. And a very good example for standardization is the Z-score. So Z-scores are standardized marks. So that's a practical way we can use the standardization. And another transformation technique is normalization. It means scaling the values into a range from 0 to 1 or -1 to 1. So in our data set, we had a variable called age, and age usually ranges from 1 to 100. So if we standardize the age, so this orange distribution here shows what happened to the variable age after we transform using the standardization technique. So now if we calculate the mean of our age distribution, it has a mean of 0 and also standard deviation of 1. And the blue distribution shows what happens to the variable age after we apply the normalization. So it's in the range from 0 to 1. So we usually use standardization and normalization only on numerical variables. And next one I'm discussing is the encoding features. Feature encoding comes into play when we deal with categorical variables. So in a data set, categorical variables can be represented as strings. For example, in our data set, if we take this variable gender, the categories are named as males and females, which are strings. But if we take this variable hypertension, the categories are denoted as zeros and 1, which are numerical variables. But if we are using this data set, if you're using this data set for a machine learning model, we need to transform our variables into numerical format because we don't input categorical information to machine learning models. So in order to transform these into numerical variables, we use encoding. So I think this encoding has been already discussed in a previous session as well, if I'm correct, but I'll explain it because it's included in this under this topic as well. So there are two types of main encoding method, one-hot encoding and label encoding. So I'll first explain one-hot encoding. So this is the categorical variables from our data set, name, work type, and there are 3 categories in this variable: private, government job, and never work. And when we are using the one-hot encoding, what we do is we create one new variable for each of the unique categories we have in our data set. So for work type, we have 3 unique categories. So when we one-hot encode our data set, it results in 3 new variables, one variable for each category. So for private, the category private, I have created a new variable called private. And since these 2 observations belong to the private category, I have denoted that using 1. And since this variable belongs to the category government job, I have denoted that using 1 in the government job variable, and rest of the variables have set to 0. That's how one-hot encoding works. And so I'll show you how we can do that using Python. I hope you guys can see my notebooks. So this is a collab notebook I'm using. And here I have loaded my data set, the data set I showed you in the slides. And this is the a part of my data set. I'm printing out using the head function. And so this is my response variable, and these are my other variables. And here, I'm not doing any data cleaning or pre-processing stuff. I'm just focusing on the techniques I am describing. But just to make sure, here I'm removing the missing values from the data set, so the process would be smooth. Okay, so as I said earlier, there are only 3 numerical variables in my data set: age, average glucose level, and BMI. So here I have used a describe function to say some description about the variables. So my age ranges from 0 to 82, and average glucose level ranges from 55 to 271, and BMI from 10 to 97. So first, I would show you how we can use the data transformation. So in the sklearn library in Python, there's a function called preprocessing, which we can use to transform our data. And how we use that is, so in the preprocessing, we can use this preprocessing function to initialize both standard scalar and the normal scalar. So I'll first show you how we can use the standard scalar. And in preprocessing, I'm using standard scalar, and I'm fitting that to my data, and I'm fitting that only to my numerical data. So here I have created a different data set using my numerical data. And then I transform my numerical data set using the scalar I initialized here. So then after transforming my data would look like an array like this. So here I'm transforming my data again into a data frame, so it would be more clear to see. Then I'm adding my skilled variables to the data set I initially had. So I initially had age, average glucose level, and BMI. And these are the transformed variables using a standardized scalar. So now this age is different than the age I had earlier. So the values are transformed. And the same way we can do the normalization. So in the preprocessing function, there's my normalizer, and I'm fitting that to the numerical variables, and I'm transforming using the scalar I initialized. And in the same way, I'm creating a different data set using my normalized variables. If anything is not clear, please ask. So I'm continuing, hoping that everything is clear. So here I had my age variable earlier, and this is the age variable after applying the normalization. So we can plot and actually see the difference. So here I'm using the library called Seaborn and also Matplotlib to do the plots. So here I'm plotting the age variable after standardizing, and age variable after normalizing. And this red distribution is how the distribution looks after standardizing, and the green is the normalized one. And here we can draw the distribution by setting this KDE to true or false in the histogram plot. Okay, and is there any questions up until now? Okay, so I'll continue. So now I'll describe how we can do one-hot encoding using Python. So I hope you guys know the pandas library. We can import the pandas library as PT. I have already done this, so I'm doing just to explain. So we can import the pandas library, and in the pandas library, we have this function called get dummies, which we can directly use to do the one-hot encoding. And here I'm doing the one-hot encoding to my data frame, where I have all the columns, all the data. And here I'm stating that I only need to do the one-hot encoding for these variables. And then I apply the one-hot encoding. And this is how the data set would look after apply one-hot encoding. So in my data set, if I take the variable gender and values, sorry, value counts. Okay, so if I take my variable gender, there are 3 categories: female, male, and other. So as I said earlier, in one-hot encoding, it create new variables for each of the categories I have. So here, one-hot encoding has created 3 variables for the variable gender. So now I have gender female, gender male, and gender other. And same happens with the other variables as well. And also, there's this concept called dummy encoding in so where we can use for machine learning. So when we do one-hot encoding, some people call it as a dummy variable trap. For there are some machine learning or statistical learning algorithms where the one-hot encoding doesn't work well. So it means when you do the one-hot encoding, for example, if we take this gender variable, let's omit this gender other. Let's think we have only males and females. So if you look at the female variable, we have zeros and ones. And if you look at the male variable, we have ones and zeros. It's like we are repeating the same thing with different numbers. So it seems redundant. So there are some machine learning or statistical models which can't actually handle this. So this association between predictive variable is known as multicollinearity. So in models like regression, they can't actually handle multicollinearity naturally inside the model. In that case, we need to remove these redundant variables. So if we had n categories, one-hot encoding return n categories. But this in dummy variable approach, what we do is if we have n categories, the dummy variable approach returns n minus 1 categories. So for our gender example, it would return only this female or the male variable. So there won't be any redundancy or multicollinearity between the variables. So in dummy encoding, there's just one simple change. We use the same function, get dummies, and we say to drop the first variable they are doing. So in here, I had 3 variables earlier in one-hot encoding, gender, female, male, and other. But after dropping the first variable, it has only the male and the other variables. So there's no multicollinearity. We can do that as well. So moving on to the slides again. Okay. So what if we have lots of categories in one feature? For example, postcodes. If we take a data set with information about people, there could be around 5,000 postcodes. So if we one-hot encode that variable, we'll end up with 5,000 new variables. So that's not good. That's not good for our models. So in that case, there's something called label encoding. It's very simple. What we do is we map each of our categories to a number. So here our private would be number 1, government job would be number 2, and now work would be number 3. It's really simple. It's just a numerical mapping to our categories. So now you might be wondering in what instances we should use one-hot encoding and in what instances we should use the label encoding. So one-hot encoding, in label encoding, we can actually use label encoding. Our variable is more of a ordinal one. For example, suppose our variable is saying something about something which has an order like low, medium, high. Sorry about my writing. Low, medium, high. So this actually has an order. So if we denote this using 1, 2, 3, it actually preserves the order of my categories. But what if we use one-hot encoding? It doesn't preserve the categories. So for instances like this, and for instances where we have like many number of categories, we can actually use label encoding. Okay, I'll show you how we can do the label encoding in Python as well. Okay. So in the same sklearn library, there's a function called label encoder. So throughout this session, we'll be using this sklearn library most of the time. And so here we can use this, you can first initialize this function, label encoder. And we can select the columns we want to encode, our categorical columns, and then we can fit the label encoder. And this is how the results look like. So for the gender, we have 1, 0, and there should be 2 as well. And for work type, some other numbers. So for each of the variables we encoded, we have only one variable as and in the resulting data frame. Okay, so that's it about feature transformation. Sorry. Okay, so let's move to feature selection methods. Okay, so what is feature selection? Feature selection is selecting most important or relevant features from a set of features. So for example, suppose there's this data set with 100 features and we want to build a model. And there might be redundant features. It means features which are similar to each other. And there might be some features which are highly dependent on each other, highly correlated with each other. In that case, we can remove some features and select only the features which is very important for our model building process. And there are a few feature selection methods which we can discuss. And today we'll be discussing about the feature selection methods under supervised learning. And I'll be explaining 3 methods: filter method, wrapper method, and embedded method. Okay, the first one is the filter method. And filter methods means we select features based on their relationship with the response variable. And there are 2 types of filter methods, Pearson correlation and chi-square. Okay. So Pearson correlation means the method we are using to analyze the relationship between 2 numerical variables. For example, this is a graph between age and salary. And let's say I want to predict salary using the age. Can I do that? In order to do that, there should be some relationship between age and salary. By looking at this graph, we can say that, okay, as the age increases, salary also increase. So elderly people have a higher salary than younger people. So there's some sort of relationship between age and salary. But can we quantify the relationship between the 2 variables? Or can we statistically say that there's a relationship between these 2 variables? To say that, we can calculate the Pearson correlation. So the Pearson correlation can actually capture how strong the association between 2 variables and also to which direction the association goes to. So the relationship between 2 variables is known as correlation in statistics. To explain it a bit more, so correlation statistics or the Pearson correlation ranges from -1 to +1. And if the correlation is greater than 0.7, we say there's a high correlation between 2 variables. So let's say here the correlation was 0.75. It means age and salary are highly associated with each other. So we can say something about salary using the age variable. And this association is positive. Why is that? Because as the age increases, the salary also increases. But there might be negative relationships as well. So here, as the age increases, the salary has decreased. It means elderly people have less salaries than younger people. So this can be denoted by the negative Pearson correlation. So if there's a negative sign in front of the correlation coefficient, we say the association is negative. So how can we use this as a feature selection technique? So if the features are less correlated with the response variable, you can actually remove them. So if my response variable is salary and my age is not that associated with salary, it means I can't use the age to say anything about the salary. So age is not important. Then I can actually remove that variable. So that's how we use Pearson correlation for feature selection. The next method is chi-square. So chi-square is basically used to analyze the association between 2 categorical variables. In this graph, I have 2 variables, stroke, and in my x-axis, I have 0 and 1. 0 means not having a stroke, and 1 is having a stroke. And this orange color are females and blue color are males. And in both instances, there are less males and high number of females. So it means so for the people who had a stroke, there are less number of males. And also for, if we consider the group of people who did not had a stroke, there are less number of males. So by just looking at this graph, we can say that there might be no any relationship between these two variables, but we can't exactly say that. So to get a statistically significant decision about the relationship between those two variables, we can do this chi-square test. So chi-square test is a test where we can use to test the independence of two events. So it say whether the difference between two categorical variables is due to chance or whether there is an actual relationship between them. In our case, we have two variables, stroke and gender. So we need to actually know whether the strokes are happening, whether the strokes are related to the gender or not. So before doing a chi-square test, we have to state the hypothesis. So our null hypothesis in a chi-square test is that two variables are independent. It means in our example, stroke does not have any association with gender. And my alternate hypothesis is that two variables are not independent. It means my two variables are related to each other. Sorry, to do a chi-square test, we need to calculate the chi-square statistics. We need to calculate a statistics called chi-square statistics. It's calculated using the observed values and the expected values. So I will explain that in the next slide. So we are trying to test the association between two variables, stroke and gender. So stroke has two categories, yes and no. Gender has, let's say it has two categories, female and male. And I can calculate the totals between the categories and create a table. So this is known as the contingency table. And this cell here says that there are this number of females who did not had a stroke. And this cell says that there are 120 females who actually had a stroke. So these are the observed values from our data set. So I said earlier that we need observed values and expected values in order to do the chi-square test. So observed values are the values we actually see in our data set. Expected values are the things we actually expect them to do. For example, if we take a coin and let's say we toss our coin 100 times and we got 70 heads and 30 tails. Sorry if this is not very clear. So, but if a coin is unbiased, we expect it to have 50 heads and 50 tails. Why? Because the probability of having a head is 0.5 and probability of having a tail is 0.5. So this is something we expect and this is the value we observe. Likewise, for this also we can calculate the expected values. So this is how we calculate the expected values. So don't worry too much about these calculations. You can actually do this very easily using Python, but I am just explaining how we can do that so you can actually get an idea about what this test is about. So to calculate the expected value, what we can do is we can multiply row totals by column totals and divide by the total number of observations. So in our case, if we want to find the expected value for males who had strokes, it means males who had strokes. So what we do is we get the row total and we multiply it by the column total and divide by the total number of people in our data set. So the value is 85.66. So the observed value was 89 and the expected value was the value we calculated, this one. And next what we do is we calculate the statistic for each cell in the table. It means we calculate the expected values for all of these cells. And then we calculate the statistics for each cells in the table. And then we get the summation and calculate the chi-square statistics. So that's basically what happens in the chi-square statistic. So I'll show you this in Python and explain in more. So you'll understand it with an example. Okay, so I'll first show you chi-square statistics because we were actually talking about that. So in Python, there's this library called SciPy, and we can use that to do the chi-square test. And as I showed in the slides, to do the chi-square test, first we want to come up with the contingency table. So this is the contingency table between the stroke and the gender. So I have my 2 categories for stroke, and I had 3 categories for gender, even though I showed only 2 in my slides. So I have the 3 categories here for the gender. And then I build the contingency table using PD crosstab, which is a function from pandas. And these are the 2 variables I want to build the crosstab with. And this is the resultant table. And then I can use this function directly, which actually calculate the chi-square statistics for us, so we don't have to do all these calculations by hand. So this is the result after we do the chi-square test for our contingency table. And this is called the chi-square statistics. And this is the p-value we get. So here my chi-square statistic is 0.27 and my p-value is 0.87. So I think the p-value was already discussed in previous sessions. So if my p-value is greater than 0.05, so we usually reject the null hypothesis if the p-value is less than 0.05. But in this case, my p-value is greater than 0.87. It means I have to accept the null hypothesis. It means there's actually no relationship between the 2 variables I saw. So if we actually look at the graph I showed you earlier, we could actually see that there's not much of a relationship between stroke and gender, because in each of the categories, the number of males were less than the number of females. So that explains by the chi-square results. So I'll show you how we can do the Pearson correlation test using Python. We can use the same library, the SciPy library, and there's the function called Pearson R, which we can directly use to do the correlation test. So these are the 2 variables I want to check. So I want to know whether there's an association between age and BMI, which are 2 numerical variables. And then I apply the Pearson R test and I tell which variables I want to actually test. And this is the statistics it gives me, 0.33. So if you can remember, I said you earlier, if my Pearson correlation coefficient is greater than 0.7, we say there's a high correlation between 2 variables. Here it's 0.3. It means there's some sort of an association between 2 variables, but it's weak or medium. And what p-value here means is it's really small. It means it's smaller than 0.05. It means there's a significant association between the 2 variables, but the association is somewhat low. That's what we can say from this value. So we can actually, without calculating the Pearson correlation for one variable at a time, we can actually do a matrix. So how we can do that is in Python, there's this function called CORR. So I can apply this function to all of my numerical variables. So in my case, I have only 3 numerical variables. So it gives us a matrix. So here I have all my variables and the correlation with all the variables. So it's easier that way. So we don't have to do the calculation each of the time. So if I take age is less correlated with average glucose level and BMI. So each of the variables are weakly correlated with each other. And also when we find out the matrix, the correlation matrix, using the Seaborn library, we can directly plot this correlation matrix using the heat map function. So it actually gives some visualization of the correlation values. And if the colors are really lighter, it means there's a very low correlation. Sorry, colors are lighter means a high correlation. Colors are darker means a very low correlation. So it's easier that way, building up a matrix and visualizing it so you can actually see the relationship between variables. So do you have any questions up to that point? Not, I can move on. Okay, seems like there are no questions, and I'm explaining very clearly, I hope. Okay. So the next topic I'm going to discuss is the embedded methods. So to remember again, there are three methods where we can do the feature selection, and we already discussed the filter method, and now I'm going to discuss the embedded methods. So embedded method means feature selection is the part of the model training. It means for each of the machine learning model, there's a feature selection method, which is related to that. So we can do the feature selection while we are training the model. So the first one I'm talking about is the lasso. So lasso is a regularization technique. We called it as a regularization technique, and we can use that with logistic regression and linear regression. So here I'm explaining it with logistic regression since we are discussing a classification problem. So I hope you guys have an idea about logistic regression. If not, all the machine learning models will be discussed in the next session. So, but I'll give a very simple introduction to the logistic regression. It's a classification technique where we can use to classify binary class problems and multi-class problems. So here in my case, I have some observations and I want to divide that into two groups. So for this kind of questions, I can use logistic regression. Sorry. So what's lasso regularization? So this part might be a little bit complicated, but don't think too much about it. Just try to grab the idea of what I'm saying. So there's something called cost function. I'll explain that using simple linear regression. If we take linear regression, let's say we have an observation y, and we predict it as y hat. So this is the actual value, and this is the predicted value. We can take the error between these two values by y minus y hat. And what if we have many observations? Then we can put an I here, and so let's say we have m observations. So we want to take the errors among all the observations and get the summation of the error. To avoid negative values, I'm taking the square, and to get an average, I'm dividing by the number of observations I have. So now I have mean squared error. So this is the error function in the linear regression. So when we are training a model, what we try to do is we try to minimize the error, or we try to minimize the cost function, which is this in linear regression, and which is this in logistic regression. This might seem complicated, so we don't have to worry about what this mathematically say. So what you have to remember is there's something called cost function, and what it tries to do is when we are training a model, we want to minimize the cost function. It means we need to minimize the error. So in logistic regression, we try to minimize this L. And what lasso does is it's a regularization technique which add a penalty against complexity. To be more precise, let's say I have three variables, x1, x2, and x3. So in a regression model, we have weights associated with each of these variables. So let's say the weight of my W1 is 0.9, and this is just 0.1, and this is 0.3. Sorry about my letters again. So the weight of the weight of the variable x1 is 0.9, which is the highest number. It means this variable is very important. And if we think about this in a linear manner, it means if we increase this x1, the importance of x1 variable to the response variable is very high because the weight associated with x1 is very high. But this variable is not that important because the weight associated with this variable is 0.1. So this have a less impact on our response variable. So what lasso do is so as I said earlier, it's a regularization technique. It's known as L1 norm. So it tries to penalize these weights. So if this variable is not much important, we try to equal this weight to 0. So this variable is completely gone. So that's what lasso is trying to do. So if we identify this variable as weakly important or not very much informative, then lasso tries to equate this weight to 0 so that this variable is gone. That's what lasso does. So I'll explain this using the code. So that will be more easy to understand, I guess. So before going to the lasso, I want to say something about the data set. And so this is the data set we are using, and this is my response variable, which is stroke. And my response variable have zeros and ones. So this is my response variable. And if I take value counts, okay, it has zeros and ones, and it has less number of observations in the class 1. So if I take that as a percentage, 95% of my data belongs to class 0, and only around 5% of data is in my class 1. So this is a very imbalanced data set. In this case, if I train a model, for this data set, my model will learn about my class 0, but it will not learn much about my class 1 because there are no enough observations. So to avoid that, I'm using oversampling. It means, so there are so there are 4,700 data points in my class 0, and I try to do random sampling and equate the number of observations in class 1 and class 0. So I'm just telling this is as a data pre-processing stop. Don't worry too much about that. So before doing the oversampling, I'm dividing my train and test sets because I don't want to do oversampling to my test set. I just doing oversampling to my train set. So my train set is not imbalanced anymore, or my train set have similar number of 0 labels and 1 labels. So before oversampling, if I take my X train set, so this is, I'll explain this as well. So in sklearn, there's this function called train test split, where we can use to split our data to a train set and test set. And this is how we use that. So we say this is our X data set and this is a Y data set, and we want to divide that into test and train set, and our test side should be 20% of the whole data set. And then I use this mod function, which is a function we use to do the oversampling. And after oversampling, this is how my train set look. So before oversampling, I had only 3,770 labels in my class 0. And in my class 1, I had only 156 data points. But after oversampling, I have similar number of data points in both of my classes. Okay, so now I have the data set. Now I'll go for the logistic regression. So if you don't understand anything on the go, please ask questions. Okay, and I'm explaining, hoping that you guys don't have any questions. Okay, so in the same sklearn library we used earlier, we can import this function called logistic regression. So, and directly we can use that to build up a model. And before using the logistic regression model, I'm scaling my data using the standard scaler, as I show you earlier in the standardizing step. And I'm again dividing my data into train and test sets after scaling the data. And I'm doing the oversampling here as well. So you guys are very clear when you're referring to this notebook later. So this is how my data set look. And I have encoded variables, my categorical variables, and I have transformed standardized variables. And now I'm going to apply the logistic regression model.
Can I ask you a question, ma'am?
Yeah.
You had just mentioned in oversampling that I think that you have artificially created the data.
Yes.
In 0 class, is that right? Because we have created some artificially data. Is that right?
Yeah. So yeah. Thank you for the question. It's not like we are creating new data. What we do is we randomly sample the existing data in our class 1. If you understood that. It means, let's say in my class 1, I have a row like this and another row like this. And I have only 2 rows, but I need 10 rows to balance out my data set. So what I do is I repeatedly use the existing these 2 rows and try to create 10 rows. So it's like randomly sampling the existing data. I'm not creating any artificial new rows. Does that answer your question?
Yeah. Yes, I got it. Yes, thank you, ma'am.
Okay.
Yes.
Okay. So why we do that is, so let's say we had only, we had 95% of data for the class 0, and we had only 5% data for class 1, as in our question. So when we train the model, my model learns mostly about this class. It does not learn much about this class. So when you are predicting, my model actually can predict this class very well, but it cannot predict this class well because it hasn't learned much about this class. That's why we do the oversampling and try to balance out the data. Okay, so moving on. Now we have our scale data set, and I'm going to fit a logistic regression model. So here I have initialized the function, and now I'm fitting to my trained scaled and Y-trained scaled data sets. And here I'm printing the training accuracy and testing accuracy. So those are not very good, 75% and 67. So this is just using the logistic regression. We haven't used lasso yet. Now let's apply the lasso regularization. So before that, we can actually print out the coefficients or the weights, as I explained earlier, by using this coefficient function. And these are the coefficients I got for all of my variables. So for all the variables, I have some sort of weight associated with it. It means none of the variables are removed from the model. All the variables are there in my model. So now I'm going to apply lasso regularization. It's not that complicated. So I have the same logistic regression function. So I'm stating that I want to add a penalty, which is L1. L1 is what we use for lasso. And here I said that my solver is liblinear. It means it's kind of an optimizer, and we can change the solver we want. And I actually include that in the here as comments. So if we are using the penalty L1 or lasso or reach, we usually use the liblinear as the solver. And also we have here C. I'll explain what C is about later. So here I'm fitting logistic regression model again with the lasso penalty. And now let's see what happens to the coefficients. Okay, so here are the coefficients. Here some of my coefficients are set to 0. It means the variable associated with each of these coefficients are gone from the model. So let's see which variables were removed. So the weight of the age has set to 0. It means age is no longer a variable in my model. And gender male, gender other, these have been set to 0. It means I can actually remove these features because they no longer has any weights associated with them. I hope you guys understood what regularization means from this. Now I go back and explain you what the C is about. So C is the regularization parameter. That's how we actually control the amount of regularization we want. And as so I'll go back to the slide for a bit. Okay. Hope you guys can see the slides. So this is the equation for the L1 or the lasso regularization. And there's this hyperparameter called alpha, which actually controls the regularization. And if I go back to my code, so the C here is the inverse of the alpha. So C equal 1 over alpha. So what happens is if we increase the value for the C, the regularization amount decrease. If we decrease the value for the C, the regularization amount increase. I'll show you how's that working. So here I have set the regularization as 0.01. Let's increase that. Let's say 1. And sorry. Okay, let's see how we did this. Sorry. Let me check again. Okay, I have my data. Okay, here my the dimension of my X set and Y set is not equal. So I'll go back and run the oversampling I did again. Sorry about that. Okay, so here I have my data. Okay. Okay. So I fit the logistic with lasso again. And I have my accuracies. And now let's print the coefficients. So if you can remember earlier, we had the first variable also set to 0. Now only 2 of my weights are set to 0. It means the regularization has decreased because I increased the parameter C into 1. So if I check now which variables are set to 0, now my age has a weight. So now age is a variable in my model. So how we can actually decide what amount of regularization we want? For that, we can actually use this function called lasso path and plot how the lasso or the regularization varies and how the weights associated with the regularization varies with that. So if I interpret this graph, in my x-axis, I have the C values, which I can use to control the regularization. And in my y-axis, I have coefficients. It means these are the weights for the coefficients. And if you look at this part, when my the C is very low, it means the regularization is very high. It means most of the coefficients are set to 0. Now, all of my coefficients are like most are set to 0. And when I increase the value of C, so my variables, some of my variables have weights. And when I increase that to a very huge number, all of my variables have weights associated with them. So we can actually use this as a feature selection method, because if we control the regularization, we can use that to drop the features which are not very much associated with our response variable while doing the training. So that's about lasso. Okay. Do you have any questions regarding that? Okay, so moving on. Next method I'm going to discuss is decision trees. Okay, I'll actually show the code and explain how we can do that. Okay, so we can use the same library we did, the sklearn, to use the decision tree classifier function. And in sklearn.tree, we have the decision tree classifier. And also, I'm importing this export graphics function so I can plot the decision tree later. So here how I'm going to fit the decision tree. So decision tree classifier, and I'm initialize this random state because as each time I do this, I fit this decision tree classifier, I will get different results. To avoid that, I'm setting my random state as 42. And then I have said that I want max depth as 3. I'll explain that later. And then I'm printing out the accuracies. So my accuracy is 71%. And I'm using the graphics library. I told you earlier, this function and the graphics library to plot or visualize my decision tree. So I have fitted this decision tree on the same data set, the stroke data set, and I had age, gender, smoking status, those as variables in my data set. So if I look at this is a root node. So this is where the split begins. So earlier we saw that we set the max depth into 3. It means we are doing this split only 3 times. So this is the first time, second time, and third time. So that's the meaning of the max depth. We can control the depth of the tree by setting values to that function. So here in my root node, the model has used the variable age. And if my age is 52, less than 52, it classifies to class 0. If it's false, it classifies to class 1. And also there are some things, as I'll explain this as well. Gini value. The Gini value means it actually says how the observations are classified in that node of the tree. For example, here Gini is 0.5. It means I have 50% from each of the classes at this point. And when the Gini value decreases, it means some class has classified in the better manner. For example, here my Gini value is 0.018. Here my class 0 has many observations and class 1 has only few observations. It means class 0 is important here in this node. So that's this Gini means. And sklearn use this Gini index, I suppose it used that, to calculate the feature importance. So this is something we can actually do using sklearn. We don't have to worry about how it's calculated. So let's calculate the feature importance and compare it with this decision tree. So in our decision tree, the first variable the model used in order to do the first split was age. So the model thinks age is the most important variable. That's why it takes age as this first variable. So let's check this feature importance, which is a direct function in the decision tree where we can print out the importance of each features. And also we can plot these features just using the matplotlib library. Okay, so as you can see here, this y-axis says the importance, and my x-axis says each of the feature names. So here, age is the most important variable. That's why it has been used in this root node to do the split. So secondly, it has used ever married and smoking status. So those also has to be important variables. So as you can see here, we have smoking status, work type, and ever married as important variables when we have the depth of tree set to 3. So we can actually use this as a feature selection method. When the features are not much important, we can actually remove them. And despite this one, we can actually look at the tree and also decide which features are important based on the place they are in the tree. So that's how we do feature selection using decision trees. Okay. So that's about the embedded methods. So now we have already discussed the filter method and the embedded method. And the final method for the feature selection is called the wrapper method. So in the wrapper method, we'll be using a predictive model to evaluate the features we have in our data set, and then we are going to select the best performing set. So how we can do that? So the first one we are discussing is forward selection. In forward selection, what we do is we iteratively build a model by adding one feature at a time. So I'm using this example to describe the forward selection. So here I have 3 predictor variables, x1, x2, and x3. And this is my response variable, stroke. So I'm going to use these predictor variables in order to predict this stroke variable. So that's my problem. So in forward selection, we start with nothing. So we don't have any predictor variables. We just have our response variable. In the first iteration, I'm going to select one variable, which is most important for the model, and select that. So how I'm going to do that? So hope you can remember we had 3 variables in the model, x1, x2, and x3. So in the first iteration, what we are going to do is we feed a model with each of the variable and response variable. So if we had 5 variables, we are going to fit 5 different models. And then after training these models, we are going to test the accuracy. So for these 3 models, let's say this one had the best accuracy, which is 87. It means when the X1 variable is associated with the stroke, the model predicts well, or the most important feature is X1 from these 3 models. Hope you can understand that. So what we are going to do next is, so we select X1 as our most important feature. Then we go back. So now we have selected already X1 as one of my features in the model. So we leave it as it is. And now we have 2 remaining features, X2 and X3. Now what we are going to do is we are going to add X2 into the model and train a model, and also add X3 into a different model with X1 and train a model. Okay. So from these 2 models, the highest accuracy is from the second model where the X3 was added with X1. So when X1 and X3 are together, the prediction is better rather than this model. So in the next iteration, so we have X1 already in our model. Now we are going to add X3 into our model. And our remaining variable is X2, sorry. So we start with nothing and we end with adding all the variables to the model. You can actually control the number of variables you are adding. So let's see how we can do this using an example. Okay. So I'll share the notebook. So we are using the same data set. And from the same sklearn library, I hope you guys can see my notebook. So I told you earlier, to do the forward selection, we need to train a model at each of the iteration. So I'm training random forest classifier. And so my model is a random forest classifier. And in Python, there's this library called mlextend where we can use for feature selection. And I'm importing sequential feature selector function from that. So here I'm using sequential selector function. So first I have to say which type of model I'm going to use for my forward selection. And my model is the random forest classifier. So I have put that here. And njobs means it's a attribute for the performance when doing the model training. And here I have to state the number of features I want at the end. So here I can say whether I want 5 features, 6 features, something like that. And I have to set forward to true, say that I'm doing the forward selection, and I'm setting this float into false. Floating is there because there are other selection approaches called as floating forward selection. So I'm not going to do that. So I'm setting that to false, and scoring is accuracy. So I'm selecting models based on the accuracy. And here I have set verbose to true. So the details will be printed while the model training is happening. So this actually takes some time. So I'll go ahead with some already printed results. So this is how the model has been trained. First, it selects the 1 feature out of 6. It means the first feature out of 6, and it prints out the model accuracy. And then it selects the second feature out of 6, and then it print out the score. And likewise, it select all 6 variables. Since we have said we need only 6 variables, it will select only 6 variables and then stop the function. So these are the, we can use kFeatureName function, which is in forward selection to print out the selected variables. So these are the variables selected by the method: age, gender, other, heart disease, work type, never worked. So these are the variables. And then we can use this variable to train the model. So what we did was we selected some variables. Now we are building our model using the selected variables. Okay, and this is the accuracy I got. I'm fitting the same random forest model to my selected variables. And these are the accuracies I got. 91% test accuracy, which is good. And that's forward selection. Do you have any questions regarding that?
Excuse me, ma'am.
Yeah.
You have mentioned earlier that we can use different models for training process.
Yes.
Is that, can you explain a bit more? I mean that why don't we use only one model for train each iterations?
No. What I mean was for each iteration, you have to use the same model. So what I meant by different model is, as the model for the forward selection process, you can use any model you prefer, like a decision tree, a regression model, anything like that. But for each iteration, you have to use the same model.
Right. Okay, thanks.
Okay. Okay, so I go back to the slides. Okay, so the next one we are talking about is the backward elimination. It's similar to the forward selection. The difference here is we actually start with all the variables and we eliminate one variable at a time. So for example, let's say we had 3 variables. And if we are starting with all the variables, first we are going to train a model with all 3 variables. And let's say the accuracy is 81%. So at our first iteration, we have all 3 variables. And in the second iteration, we are going to remove one of these variables, either x1, x2, or x3, depending on the depending on the accuracy of the models. So this is how we are going to do that. So we started with x1, x2, x3. First, we are going to remove x1 or eliminate x1 and train a model, then eliminate x2 and train a model, and eliminate x3 and train a model. So we are going to eliminate each of the variables at a time and train model for each of the instances, and then test the accuracy. So as you can see here, we have a very good accuracy when we eliminate the variable x2. It means that the first iteration, we are going to remove the variable x2. So that's how we do the backward elimination. And you might be wondering why we have 2 methods as forward selection and backward elimination. So for example, for example, let's say we had 100 variables and we prefer to have 95 variables in our final model. So if we go ahead with forward selection, it means the method is very exhaustive, or it's very computationally exhaustive, because going from 1 to 95 is a long way. But if we go for backward elimination, it means we have to eliminate only 5 variables to reach 95. So it works the other way around for the forward elimination. So we can actually select the method we want to use based on the way we want it to use. So I'll show you how we can do that in Python. It's very similar to the forward selection. Only difference is, so as you can remember, in forward selection, we set this to true because we want to do forward selection. In backward selection, we set this to false. So in that case, it will run the backward elimination. So what it do is, here I have I want 10 features at the end. So it starts with all the features and it reduces the number of features until 10 features is remaining. So that's what it do. And these are the remaining features. And this is the accuracy. So in both of the cases, we actually told the model to give us this number of features. We exactly specified the number of features we want. But sometimes we actually don't know the number of features we want. So in that case, we want a different approach to select the number of features we want. So what we're going to do is, so in forward selection function, we have this function called get metric dictionary. And it's a very messy one because it's a dictionary. Here I've converted it into a data frame. So what it shows is, I have done this for my backward elimination method. So in backward elimination, it starts with all the variables. So we have all the variables in our first row, and going forward, it eliminates some variables. As you can see here, some variables are eliminated here. And this dictionary have all the information regarding the backward elimination process. So we can actually plot a graph with the number of features and the performance. So here I have fitted only with up to 10, from 10 to 16 features. But if I used 1 to 16, something like that, you can see a more different graph. But here, I have number of features and the performance, and based on this, you can actually see for which number of features the selection method gives the best performance. So you can use this. Else, what you can do is, rather than giving the number of features you want, you can actually say, I want the best number of features. You can use that to specify that you don't know the number of features, you just want the best number of features. So it will automatically calculate and give you some number of features. So that's how you do that. Then you don't have to say the number of features you want beforehand, before running the method. Okay, so that's about the backward elimination. Okay, so the next method we are going to discuss is the recursive feature elimination. So, okay, so what we do there is, there also we use a model to select the features. We first train a machine learning model, and then we try to obtain the feature important like we did in our decision tree. And then we remove the least important features, and we retrain the machine learning model with remaining features, and then we repeat the process until we end up with a satisfactory amount of features or number of features we want. So how can we do that in Python? Okay. So in the same sklearn library, in the feature selection, there's this function called RFE, where we can use to do the recursive feature elimination. So here I'm using the same model, random forest classifier, to fit the RFE. RFE means recursive feature elimination. And okay, so let's see how we can interpret the results from recursive feature elimination. So if I'm going too fast, let me know so I can explain things you want to know. Okay, so after fitting the recursive feature elimination, so here I have stated that I want to select only 5 features. So what it do is, it actually rank the features according to the feature important. Here, as you can see, the age, it has been selected and its rank is 1. And my average glucose level, it has been selected, its rank is 1. So all the variables with the rank 1 have been selected by this feature selection method. And the others are ordered in the order where they were eliminated. And if we take these 11 or 12, so gender other, it's the variable which have been eliminated. I think, yeah, it's the first variable which have been eliminated because the rank is highest in that variable. All the variables with rank 1 are selected by the model. So we can print out the variables which have been selected by the model by using the get feature names out function. Okay, so can we do this manually? So I'll show you in these slides. Hope you guys can remember we actually use a function to get the feature importance in the decision tree. So likewise, we can do the same with the random forest. So these are the variables I have in my data set. So this is just an abstract because here I'm not mentioning any of the one not encoded one so it's easier for us to interpret. So this is my response variable and these are my predictor variables. Let's see whether we can do this manually. So we train a machine learning model first and then we plot the feature importance. And as you can see here, this variable here, heart disease, it's the least important feature according to this. So we can actually eliminate that feature. And in the next iteration, we can retrain the model without heart disease and with all the other variables, and again check the feature importance. And if there are very less important features, we can again remove them and train the model. So that's how you do the recursive feature elimination. Okay, any questions on that? Okay, I hope
Excuse
there are no,
me.
yeah.
How do we decide which amount features that we are going to reduce? How do we decide? Like,
You mean as we did in our previous instances, right?
yeah.
Yeah, it's actually based on the accuracy of the model. Like, think you eliminated 2 features, and so I go back. So think you eliminated 2 features, and for the second model, you got like an 85% accuracy. And now you're going to train another model where you get, let's say, 88% accuracy. But in the next instance, you get around 72% accuracy.
Right.
Right? So it means after eliminating the feature related to this model, you get a less accuracy. It means there's no point of continuing the elimination of features now. You can go ahead with this model with the best accuracy. So you can use that as the stop-in rule.
Yeah.
Okay.
Yeah, thank you. Thanks, man.
Okay. So, okay, so that's it about the feature selection method. We talked about wrapper method, filter method, and embedded method. And now let's go ahead with dimensional reduction methods. So dimensional reduction means we are reducing the number of input features in training data, but not by eliminating any features like we did in the feature selection method, but by dealing with the dimension. So the first method we are going to talk is principal component analysis, which is known as PCA. So what these do is, so it transforms the original features into a new set of features, which are known as principal components. And these are some characteristics which are important about PCAs. So I'll explain this later, but now I'll just state the characteristics. So PCAs are orthogonal to each other. It means, let's say, imagine them as perpendicular to each other. And also they always try to maximize the variance and reduce the dimensionality. So you will understand that after I explain. So I'm using a different data set to do the PCA because we do the principal component analysis on numerical variables. When we have a high number of numerical variables, we try to reduce the dimension by doing the PCA. But in the data set we were using, we had only 3 numerical variables. So there's no point of applying PCA to that. That's why I'm using a different one. So this is a breast cancer data set. So you guys might have come across this data set. This is a very popular data set. So this data set have 30 numerical variables, which are some information about cells. And there's this response variable, which says whether each observation is benign or malignant. So that's about the data set. So number of columns is 30. So let's say I want to reduce the number of dimension, and I want only 5 features. So now I'm going to apply PCA and come up with some features which actually explain the variation captured by all these 30 columns. So how can I do that? So I first explain what this dimension reduction is. So let's say we had a data set which is 2-dimensional. And let's say this is my data set. So if I look across the X2 axis, so my data set has spread like this. I'm talking about the spread of the data, how my data is spread. But if I take the X1 axis, the spread is really low. So if I want to fit a line which actually captures the variance or the variation of this data, the spread of the data, I'm obviously going to fit a line like this to this side in the middle of this data. Why? Because the data spread is really high. along this axis rather than to this axis. So if I want to, okay. So to capture the most of the spread or the variance, I'm going to fit a line like this. And to capture the least, the second highest variation, I'm going to fit a line this. So these lines are perpendicular to each other. That's what I said earlier about being orthogonal to each other. So here, these are two-dimensional data set because I have data along x1 and x2. And what if I want to reduce this to one dimension? So I can actually plot this information in this line. So this is one dimension one. So I'm neglecting this part that my data is spread across this axis as well. I'm neglecting that part and I'm transforming my data or projecting my data into a 1D plane. So that's a just basic idea about how we can reduce the dimension. So we actually projected something in a 2D plane to a 1D plane. Now it has only like a one coordinate point, to be more precise. So in principal component analysis, we do something like that. We have a high dimensional data and we are going to project it into a low dimension. So here, let's say I have some data points and these data points are spread to this direction. So if I want to capture the highest amount of variation of this data, I'm going to fit the line like this. So this is known as the best fit line. This explains most of the spread or the variance of my data. And if I want to fit another line, which explains variance, which is lesser than this, lesser than the variance explained by this data, I'm going to fit a line which is perpendicular to the best fit line. So this is my second line, which is going to secondly explain the variance of my data. So these are known as principal components. My first best fit line is my first principal components, which accounts for most of the variation of my data. And my second line, which is perpendicular to this one, is my second line, which is explain next amount of variation of my data. So I can explain it using the data set. So it will be more clear. Sorry. Okay, so as I said to you earlier, I'm using the best breast cancer data set to do the PCA, and it has this 30 number of columns, and this is the response variable, malignant and benign. So that's about the data set. Okay, so here I have my data set as a data frame with all my 30 columns, and I'm standardizing my data before doing the PCA because PCA actually sensitive to the scale. So I'm using a scalar to standardize data before doing the PCA. So in the same scalar library, I can use the same library to do the PCA as well. So there's this function called PCA. And in PCA, I can tell the number of components I want. Here I have specified that I want exactly 2 components. And then I'm fitting it to my scale data. So I'm fitting this only to numerical data. Okay, and I'm transforming using the PCA function I already fit. And this was the shape of my data before fitting the PCA. I had 569 observations and 30 columns. And this is the shape of my data after fitting the PCA. Now I have 2 components or 2 columns and 569 observations. This is how it looks, my 2 PCAs. So you don't have to worry much about this array. So think of it as 2 new features. So after fitting the PCA, we want to know the amount of variance explained by our PCA. So these are the amount of variance explained by each of the PCAs. My first principal component explains 44% of the variance explained by the data. And my second principal component explains 18% of the variance explained by my data. So roughly, these two together explain around, let's say, 64 or 62% of the variation of my data, which is good. So now what I can do is, so before that, so here I have plot the principal components This is my first principal component, and this is my second principal component. These are my observations in my data set. So here is my class. So the blue one belong to class 0. The orange dots belongs to class 1. As you can see here, my PCS could actually distinguish between these two classes. If I draw a line here, it can actually distinguish in a better manner these two classes. So how we can use these principal components to train a model? Now we don't have the 30 columns. Now we have only the 2 features we got by the PCA. And if we are going to train a model now, we use our PCAs as the features of our model. So here I am fitting a logistic regression using my PCAs, 2 PCA features I obtained from the principal component analysis as my X features. So now I have only 2 features instead of 30 features. So this is the accuracy I got, which is very good, 92%. Okay, so earlier when we are doing the principal component analysis, we exactly said we want this number of PCAs, but that doesn't work all the time. So how can we say otherwise? So here we can say that to PCA, we can give a number like this. This is 95%. The meaning of this is we are telling PCA to give us some number of components which explain 95% of the variation of my data. So when I do that, it fit it to the data and it gives 10 components. So I need at least 10 components to explain 95% of the variance of my data. So if you look at the explained variance by each of these components, so these are my first 2 components as earlier, and my third component explains 9% of the variation, and the fourth column explains 6% of the variation. And you can select number of components based on what you're working on using either of these methods. Okay, and here I have again fitted the model using the 10 components. So here my accuracy has again increased to 98%. Okay, that's how we can use principal component analysis. Any questions regarding that? Okay, so I'll move on to the last method we are going to discuss. So this is TSNE. So this is known as T-distributed stochastic neighbor embedding, which sound very scary, but it is also a dimensional reduction technique, but it's kind of different. We can't actually build up some components and use them to train the models. That's not advised to do using the TSNE. It's more of a like something we can use to discover patterns or clusters or identify some patterns. So it's something we can use visually, not something we can use like PCA. But TSNE was found around in 2008, if I remember correctly. So yeah, it's something latest, and many people use it as some state-of-the-art technique to visualize the dimensions when we have high dimensional data. So it's a nonlinear technique for dimensional reduction, and I'll explain this and what neighbor and embedding mean in here. So that might help you to understand TSNE better. So if we take a data set like this, let's say the data is scattered all around, and there are some data gathered together. And if we consider this as X, and all the data points which is closer to X are known as neighbors. So these are neighbors. And what does this embedding means? It means, I hope you can remember I showed you how we can go from a 2D to 1D. Likewise, we can go to, if we want, 3D to 2D. So TSNEs do something like that. It goes from D dimension to 2 dimension. So D dimension, it's something very hard to think about. It's like, let's say we had 10 dimension of data. It's not easy to draw or plot and see, visualize. It's hard to visualize. So, but if it's in 2 dimension, we can actually see what's really happening. So what TSNE do is it helps us to reduce the number of dimensions and see visually in a 2 dimension. So if we go from 3D to 2D, Let's say we have X, Y, and Z. And if we take a point like this, it has 3 coordinates, X coordinate, Y coordinate, and Z coordinate. And if we project this into a 2D space, let's say it's X dash. Now this will has 2 coordinates. So this is known as embedding of this X observation. So it's very simple. So I just explain it, so it will be very helpful when I'm explaining the process. So in TSNE, when we are doing TSNE using Python, there's this parameter called perplexity, which we can use to control the number of neighbors we want to preserve. So you'll understand that when I show you the explanation in Python. Okay. So for TSNE also, we can use the same library, sklearn, and we can just feed the TSNE as we did with the PCA. And we have to say the number of components, and the perplexity is the one I described in the slides. So this tells about the number of neighbors we want to preserve. It means, okay, so after fitting the TSNE, we would get 2 components like we did in the PCA. So instead of the 30 variables, we now have 2 features. We can plot these and just look at the linear relationship between the non-linear relationship between them. So here 0 and 1 are my 2 classes, and you can see how each of these observations are distributed and how it has divided into classes. So by controlling the perplexity, we can actually control how these neighbors are gathered together. If we sorry, so I have these other few things I loaded, so you guys can try this after this session as well. So this is not something very straightforward. You might be wondering why we are learning TSNE. We can't use that to do the modeling stuff, things like that. But this is something actually people use, and it's very popular to visualize high dimensional data. Think about it in that way. So this is a website. I will actually include this in the reference where you can check how when we change each of the parameters in TSNE, how did things change. So this is when we set the perplexity to 6, and let's increase the perplexity and see how neighbors are gathered around. It's like the number of neighbors gathered around increases when we increase the perplexity. And when we decrease this, it's like number of clusters get increased because the number of neighbors who gathered together decreases. It's something like that. And also there's this interesting blog about TSNE. And I hope you guys know about this data set called MNIST. It's a very popular data set where we used to predict some images which are about numbers. So we have some images, let's say this one, and we want to tell whether it belongs to a number from 0 to 9. And this is a TSNE done on the MNIST data set. And as you can see here, in MNIST dataset, we have 10 classes, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And for each of the classes, this TSNE shows a cluster. So this is for 0, this is for 6, this is for 1. And also inside these clusters, this is a cluster for 1. Inside these clusters also, we can see how this one changes. One is a straight line sometimes one is like that one we get when we type in a document. We can see these differences. So treat TSNE as something we can use to visualize and see a high dimensional data set in a 2D space, so we can actually have more information, or we can actually see clusters, something like that. It's not something much similar to PCA, because PCA we can actually use to train a model afterward, but we can't use that with TSNE. So that's about it. So that's about dimension reduction. Yeah, and we are reaching to the end of our presentation, the session. If you guys have any questions now, you can ask. Seems like there are no questions. So I'll actually post these references I used for the TSNE and all the other things and the notebooks in the slides, so you can later access them, right, Rashmi? You
Yeah,
can share this with them, right?
yeah. Miss Sandamali, there is a question in the chat box. Is there
Okay.
no way to handle categorical variable using PCA?
No, you can't use a PCA for categorical variables. It's only for numerical variables. I can't actually see any questions in the chat. Okay. Any other questions?
Excuse me, ma'am.
Yeah.
Uh, is this dimensional reduction concept related to feature selection? Is this related? I mean that what I'm thinking is dimensional reduction is kind of removing unnecessary features. Is that right?
Okay, so let me explain that. So feature selection is removing unnecessary features. It's like we eliminate if our features are not very much relevant to our response variable. So that's feature selection. In dimension reduction, what we do is we don't exactly remove any exact features. We just try to reduce the number of features. We don't eliminate anything. We try to create new number of or new set of features which actually captures the variation explained by all of the features we had in our data set. It's something like that. So after we do the dimensional reduction, we have new set of features like A, B, C, D. Let's say those are our new features. Then we don't use the features we originally had in our data set anymore. We train our model with the features we extracted using the dimensional reduction method. So that's the difference.
Yeah, you are telling that we don't remove the features. We just keep all the features, but we use different features, like that kind of thing.
Yes, so let me show you. So here, okay, I'll share my code again. So here, after doing the PCA, so there's the data set. So after doing the PCA, I have only two features. So this is the array. So I have only two features after doing the PCA because I stated that I want exactly two components. Now in my data set, I have the 30 columns I had earlier. But for model building process, I'm using the newly built two PCAs. I'm not using the data I used to create the PCAs. Is that clear for you? Why we do that is, so if we, let's say all our 30 columns are very important to us, we don't eliminate any of the features, but it's too much for us because there are 30 features. So we want to reduce the features and we don't want to eliminate any of these at the same time. So we are trying to build a method which captures all of the variation in our 30 columns, but our new method have only few features, if you understand that.
Yeah.
These PCAs together capture the variation explained by all of my 30 variables.
But we use some important features.
We use the principal components we extracted.
Right.
It's like we don't, from here, from these 30 features, we don't select what feature is important, what is not. We don't do that. We just use these 30 features. We try to grab all the information in these 30 features, and we try to project that into our principal components. So when we use the principal components, we will have all the information where was in this data set in the PCAs. But at the end, when we are building the model, we are dealing with only two features because we have only two principal components. But that two principal components have all the information about these 30 features.
Okay, good.
Yeah, so there's another question in the chat. Should we remove outliers before using PCA? Yes, because PCA is very sensitive to scale, as I said earlier. And so we don't need any surprises. Like, let's say there's in the slides, so I'll go back to my slides. I hope you can remember this one. Okay, here. So let's say we had some outliers here. It means my spread changes or my variance changes. So the direction of the variance also get changed. So if these are actually outliers, so I don't want any impact from these observations to my PCAs. In that case, I can actually remove them. So yes, we need to remove outliers before using PCA. So to remove outliers, it actually depends on the data set, I would say. Like, to remove outliers, there are various methods. We can use either IQR, or we can manually spot outliers and remove them if there are only one or two outliers. But it actually depends on your application, because sometimes, let's say from the IQR, we might remove like a many number of observations, or we might have another method which removes only a part of the observations, which actually doesn't impact our analysis. So it actually depends on the applications you are using. And if there are only like one or two extreme values, you can actually manually pick them and remove by hand. So it depends on what you are doing. But for the PCA, you need to remove the outliers. Yeah. So any more questions?
I have another question.
Yeah.
You have mentioned earlier in that dummy variable
Yeah.
techniques. If we take female and male,
Yes.
you have to reduce only one, either female or male
Yeah.
variable, because of the multicollinear happens.
Yes.
Can you explain how that thing impact to the dependent variable?
Yes.
Yeah.
So let's say I have both male and female. 1 0 1 0. You're talking about instance like this, right? So when there's multicollinearity, it means my predictor variables are dependent on each other. And these both predictor variables can explain my dependent variable in the similar manner. So in this case, it's a redundant variable, which actually increase the multicollinearity at the same time, and also the model complexity. But this impact only for like linear methods, like for regression, because if we do this in Python, they can't actually handle the multicollinearity naturally from inside, because the way their cost function is working. But if we take machine learning models, they can actually handle multicollinearity. So it doesn't matter whether we have in one-hot encoding, whether we have some dummy variable which shows redundancy, this will handle multicollinearity by itself. So in that case, we don't have to do the dummy encoding. We can go ahead with one-hot encoding. So does that answer your question?
Yes. Yeah. Thanks.
Okay.
Miss Sandamali, I think
Yeah.
the Q&A session can be ended, right? Because
Okay.
yeah. Yeah.
Okay, so I guess there are no more other questions, so we can wrap up the session, right, Rashmi?
Yeah. As we wrap up today's workshop, I would like to express our gratitude to Miss Sandamali Wickramasinghe, PhD candidate from City University of London, for her valuable insights, and to all of you for your active participation. Before we end this meeting, I would like to request everyone to switch on your cameras to take a picture of today's session. Okay, thank you everyone. We hope you leave today's session with a deep understanding of data science and machine learning. Do not forget that we have more exciting sessions lined up, so mark your calendars and stay tuned for more updates on our upcoming events. Thank you everyone for joining today.
Thank you everyone for joining and for all your questions.